Hello everybody, so in 8.1 we're going to look at how to use calculus to find lengths of curves. So we know how to find lengths already of some very particular curves. So for instance, straight lines, we can find the length with Pythagoras theorem, or circles, we can find the length as 2 pi r. But these are just very special cases. How do we find the length in general? So here is the idea. The idea is that as usual in calculus, if there is something we don't understand, we can try to split it up into smaller pieces, work on each of these separately, and then at the end add them together. So let's see how that's going to work for finding lengths of curves. So we start with a curve, we want to find its length. First, we split up the curve into lots of small pieces. So we just pick points to divide the curve up into lots of bits. And then we approximate each of these bits by a straight line. So we approximate the curve by lots and lots of little straight line segments. I'll draw the picture in class. And then we add the lengths of those line segments together. And altogether, that's going to give us an approximation for the length of the curve. And the more segments we use, the better the approximation we get. So you can see there is going to be a limit in there. We take the limit to get the true length. So why do we have to do this splitting? If you imagine you have some curve that you draw, say y equals x squared or whatever curve, if you approximate your curve by just one straight line, it's not going to be a very good approximation unless you started with a straight line in the first place. But if you approximate with, say, 100 small little line segments, you can get a pretty good approximation for your curve that way. So that's why we split before we approximate by line segments. The more line segments, the smaller line segments we use, the better the approximation is. In the end, when we take a limit, we get the true value. So there is going to be a formula at the end of this that we're going to repeatedly use, but let's see how it arises. So how do we normally represent curves in calculus? We represent them by, say, y in terms of x or x in terms of y. Or if we're feeling very fancy, we might use implicit equations, something like that. But let's suppose we're in the simplest case. We have a curve y in terms of x. So the curve is just the graph of the function. How do we find the length of this? So we want some formula in terms of x using calculus, hopefully. So we said the first step was to divide our curve into lots of little bits. So we've seen before how to divide an interval, AB, up into lots of little pieces. We split AB up into n subintervals of equal width delta x, which is b minus a over n, and we number the endpoints as the xi. So this is something we've seen before many times when we define the interval or define the integral, or when we investigate properties when we're going to use integrals. So this is the same as normal. And then on each of those little bits, we're going to find an estimate for the length of the curve. So in each of those little pieces, we choose a line segment which just joins the xi minus 1 to xi. So for this ith subinterval, we look at what is the change in x of the curve, what is the change in y of the curve. And then once we've done that, we can use Pythagoras to find the length of the line segment which joins the endpoints. So in this interval, the change in x is just the length of the subinterval. That's going to be delta x. The change in y is the function at the right endpoint, f of xi, minus the function at the left endpoint, f of xi minus 1. So we just subtract the y values. That gives us the change in y. But for reasons that are going to become clear in a second, it's going to be helpful if we use the mean value theorem to write this as f prime at xi star times xi minus 1. So remember, the mean value theorem said that if we have a change in our function, that's equal to the derivative at some intermediate point times the length of the interval, right? F of b minus f of a equals f prime of c times b minus a. Okay, and here xi minus 1 is just delta x. So if you remember the mean value theorem, that's what we're using here. Otherwise, just take it as granted. Here, xi star is between xi minus 1 and xi. It's a sample point. Okay, now we know the change in x and we know the change in y. We can find the length of the segment which joins the endpoints. That's going to be our line segment. We just use Pythagoras theorem, right? We do the square root of the change in x squared plus the change in y squared. That gives us the length of the hypotenuse. Okay, here they both have a delta x squared. We can bring that out. So if we factorize out the delta x squared and then we take the square root, that gives us a delta x. And we're left with just the square root of 1 plus f prime at xi star squared. So this is the length of the ith little interval, or the ith little segment. And then if we add them all together, we get an estimate for the length of the curve. So this is our estimate. And this should hopefully remind you of something from Calc 1, right? It looks a little bit like a Riemann sum. So here we have some mess in terms of xi, or some mess in terms of xi star, where xi star is in the ith interval. And then we have times delta x. So these were things called Riemann sums. And when we take a limit as n goes to infinity, we normally get an integral. So if we do that, we do in fact get an integral. And here is the key formula that we're going to need to be able to use throughout the section. So the length of the curve, y equals f of x from x equals a to x equals b, is, notice the sum became an integral and the delta x became dx and so on. So we just need to do the integral from a to b of the square root of 1 plus f prime of x squared dx. So normally it's pretty easy to use. As long as you remember the formula, all you have to do is substitute in your, find dy dx, find f prime of x, square root, add 1, take the square root, and then integrate that. So it's just a computation, an algebraic step to find what is the inside, and then it's an example with integration. Sometimes though, the square root gives us quite tricky things to integrate. So in practice, unless it's a simple example, it can be quite hard to find the arc length. But most of the examples we see are going to be things that are actually computable. Okay, another way to write this is just the integral of the square root of, instead of writing f prime of x, we could write it as dy over dx. So square root of 1 plus dy over dx squared dx. And it's useful to write it in this way sometimes because right now we're working y in terms of x, but we could play the same game with x's in terms of y, and then just all the x's and y's will get swapped. So we'll see that in a second. So having dy over dx really demonstrates that we're differentiating y with respect to x, whereas in a second we'll do it the other way around. Okay, so let's do an example. So here is our key formula. Please put this on your formula sheet if you have one. So y is x to the 3 over 2, and we want to find the length of the curve between the points 1, 1 and 4, 8, both of which lie on the curve. So all we have to do is find the square root of 1 plus dy over dx squared and integrate it. So dy over dx is 3 over 2 times x to the half, differentiating with the power rule. If we square that, we're squaring both terms, we get 9 over 4 times x. The square root of x all squared gives us x. Okay, so we substitute in for the length, the integral. We have the integral between the x values. The x values are 1 and 4. Take care to pick, right? If we're integrating with respect to x, we use x values in our integral. If we're integrating with respect to y, we use y values for our limits. Okay, and we calculated the square root of 1 plus dy over dx squared to be 1 plus 9x over 4. Okay, and then this is just a standard integral you could do. For instance, the inside is linear, so the substitution u equals 1 plus 9x over 4 is going to work out nicely. Du becomes 9 over 4 dx, so dx is 4 over 9 du. Okay, you can transform the integral. This is nothing new. I think I'm going to skip over this step. Just a substitution, plug in the limits, and integrate, plug in the limits, and subtract. So the only new step is you have to remember what is the right thing you're going to integrate, which is the square root term. One word of caution is that remember that the square root of a sum is not the sum of the square roots. So for instance, we cannot just do the square root of the first piece plus the square root of the second piece. That's a really common mistake. So remember, you cannot just square root a sum. You have to do something else. Okay, I mean, you cannot just square root the terms individually. Okay, so let's see what happens if x is in terms of y. Everything is pretty much the same. If the curve is expressed x in terms of y, and y is between c and d, then we integrate the square root of 1 plus the derivative squared. And I think here it's more useful to think of it in this way with this formula. We integrate between the y values. So if we're integrating with respect to y, the limits are the y values. We integrate the square root of 1 plus dx over dy squared dy. So instead, we have to differentiate x with respect to y, square it, add 1, and then do the square root, and so on. So everything is pretty much the same, just with the x and the y's swapped around. Okay, for example, here's a curve. X is 1 over 8 y to the 4 plus 1 over 4 y to the minus 2, and y is running between 1 and 2. And this example is also going to highlight an algebraic step that's kind of useful, but only works in very special cases, but it's good to be aware of. So x is in terms of y. We want to find dx over dy. We just differentiate with respect to y. That's a half y cubed. So if we differentiate y to the 4, we get 4y cubed divided by 8 is going to go as a half y cubed. If we differentiate the y to the minus 2, we get minus 2y to the minus 3. We multiply with the 1 over 4, we get minus a half y to the minus 3. Okay, then we have to square it and add 1. So if we square that, remember there are going to be several terms because we also have the middle term. We square the first term, we get 1 over 4y to the 6. And then if we multiply these two terms together, we get a quarter times y cubed times y to the minus 3. So we get a quarter, minus a quarter rather. And then there are 2 times that these get multiplied together, remember? So we get 2 of the middle term. So minus a quarter gives us a minus a half. And then on the final term, we have minus a half y to the minus 3 all squared gives us a quarter y to the minus 6. And then we have to add 1, and then hopefully take the square root of that. So if we add 1, we started with a constant of minus a half. If we add 1, we end up with a constant of plus 1/2. So we have 1 over 4 y to the 6 plus a half from adding 1, plus the same 1 over 4 y to the minus 6. And now we need to take the square root of this. And this is a huge pain if we don't see a trick here, because integrating the square root of this looks really tough, especially because, as we remember, the square root of a sum is not the sum of the square roots. So we can't take the square root of each piece separately. So the trick here is we have to recognize it as a square of something. So how can we recognize this as a square of something? If we notice that these two terms look very similar, the only difference is that the minus here is replaced by a plus here. So if we cast our minds back to where this came from, this term above came from squaring a half y cubed minus a half y to the minus 3. And we're saying now the thing we want to take the square root of is the same, but with the minus a half replaced by a plus 1/2. So we might hope that this comes from squaring the same thing as before, but with the minus replaced by a plus. So we kind of hope and then check that a half y cubed plus a half y to the minus 3, so with the minus replaced by a plus, squared is equal to the thing we're after. And if you multiply out, it is true. So we can write this as a perfect square. And now the advantage of having written this as a perfect square is that when we take the square root of a square, they just cancel each other out, right? So we're not taking the square root of each piece separately, but we're doing the square root of something squared. Okay, it's just the something on the inside. So this is a half y cubed plus a half y to the minus 3. Okay, and now that we've managed to simplify that, we can integrate it from 1 to 2. So keep in mind, since we're working in terms of y, we're using y values. So y is running from 1 to 2. And there are lots of boring steps here. We're just using the power rule. We sub in the limits, we subtract them. I'm going to skip over those steps. In the end, the answer will be 33/16. Okay, so far we saw how to find the length if the curve is y in terms of x, if the curve is x in terms of y. There's just a formula we need to use involving square root of 1 plus dy over dx squared. We want to be careful simplifying the square root. One technique is to use, say, in complicated examples, is to use this completing the square idea. Okay, the last thing in this section is the arc length function. So instead of finding the length between 2 points, say from A to B, sometimes we're interested in how far, the so-called how far function. So the arc length function is going to give us the length of the curve when the endpoint is a variable. So instead of, say, integrating up to 2 or finding the length up to 3 or finding the length up to b, we might be interested in finding the length up to x. And then afterwards, we can plug in different x's to find different lengths. So kind of like with fundamental theorem of calculus when we integrate from a to x. So here we just use the same formula, except we want to find the length from a to x, where x is going to be a variable. So rather than from a to b, we're going from a to x. It's the same formula, but because the x is already used here, we cannot use x again on the inside. So we change the x to a t on the inside for our variable of integration. So everything is the same, but the upper limit is an x, and the x's on the inside get replaced by t. So this gives us a length up to a point x, and then we can sub in different x's to find different lengths. So let's see an example. Find the arc length function for 2x to the 3 over 2, starting at 1, 2. So kind of a similar example to before, just change the constants. So if we do dy over dx is going to be x to the 3 over 2 becomes 3 over 2 x to the half multiplied by 2. We get 2x to the half, and then we get 3x to the half. And then we square 3x to the half, we get 9x. So if we do the square root of 1 plus dy dx squared, we are going to get the square root of 1 plus 9x. Okay, so, and then the arc length formula, all we have to do is integrate from 1 up to x. So here we were starting at 1. We're going up to x. And then we're not allowed to use x again on the inside. So in the integration, we change the x to t's. So rather than using the square root of 1 plus 9x, we replace the x by a t. We get the square root of 1 plus 9t dt. Okay, and then we could evaluate just as normal. The x doesn't really play a role. We just use fundamental theorem of calculus, plug in the endpoints. We get our formula s of x for the length up to x. And then, for instance, if you wanted to find the length from starting at x equals 1, going up to x equals 2, you could plug in 2. If you want to find the length running up to x equals 5, you could run in 5. Rather than doing the integration again, it's just one function that captures everything. Quick sanity check, if we were to plug in x equals 1, here we would get 10 to the 3 over 2 minus 10 to the 3 over 2, which is 0. So we would be saying the length is 0. Okay, that makes sense. If we start at x equals 1, then the length up to x equals 1 is just 0. Okay, so just three things to keep in mind, all similar formulas. If we're finding the length where the curve is y is in terms of x, if x is in terms of y, or if we're finding the length up to x, in which case the same formula, but we have to switch the letters around. Okay, thanks everyone. See you next time.